Science Education Consultants. Here we are, ensuring that you continue studying. We offer a number of services that you shouldn't miss. Just visit us on our platforms, visit us on any of those contacts, and keep learning with us every day from your homes. And make sure you follow all the SOPs and remain safe in these challenging times. Teacher Ambassador Osbert, and we are continuing from our chemistry of liquid mixtures. In our previous video, we tried to use Raoult's law to calculate some compositions of different liquids and vapors, and I left you with an exercise. I received some answers. For those who have not yet answered, please make sure you keep following and keep answering. Keep forwarding for us those answers, and we keep in touch. Today we are just going to continue with Raoult's law. Like we said, Raoult's law only applies for a few liquids which are called ideal solutions. Those liquids which you can mix, and when you mix them, they form ideal solutions. And we say that Raoult's law simply states that the partial vapor pressure of a liquid is equal to the product of the mole fraction of a liquid in the solution and its vapor pressure when it is in its purest form. Those vapor pressures of pure liquids are in literature. They have been determined. They don't need to be determined experimentally. They are in literature. They are stated already. They are constants. So they are always known. And you can easily find the concentration of anything in the solution. And so it becomes easy for us to know the content of any vapor. We say that those liquids that obey Raoult's law, for us to use this formula, we must have an ideal solution. So today, we are going to answer this question. What is an ideal solution? By the end of today, you should be able to define and state characteristics of an ideal solution, and you're supposed at least to know how to draw the composition diagrams of ideal solutions. So an ideal solution, we say, it is always formed when you have mixed two liquids, and in mixing them there is no change, there is no significant change in the interactions of the molecules. That's why there are very few liquids which you mix and they form ideal solutions. Yesterday we used an example of hexane and heptane. Hexane and heptane. We said these are two liquids which are both alkanes. They are both non-polar, meaning that the way heptane molecules interact when they are in pure heptane and the way hexane molecules interact when they are in pure hexane may not be far different from when the two molecules interact together when you mix these two liquids together. And therefore, if there is no significant change in the interaction, it means that the hexane interactions, these are the cohesive interactions. Let's use what we know, cohesive forces. And the heptane interactions, they are still the cohesive forces. And then the hexane interactions, these are now the adhesive ones. all of them should be uniform. They should be uniform for us to have Raoult's law obeyed. And if they are uniform, that means that when you mix these two liquids together, it's as if you have mixed the same liquid. It's as if you have measured water in 1 cup from the jerrycan, and you have poured the same water from the same jerrycan in another cup, and you have mixed them together. There is no difference between these two liquids when you mix them together. Always when you mix 1 cup of water with another cup of water, you get 2 cups of water. So the volumes must be additive. And because the interactions still remain uniform, there is no any energy change. There is no heat gained, there is no heat lost, since there is no change in the interactions of the molecules. So those are the few characteristics of an ideal solution. There are few liquids, I will continue saying it, that can have these properties. So, can we briefly define an ideal solution and we proceed? Feel free to take note. So, this is the definition or the meaning of an ideal solution. A solution formed in a way that it obeys Raoult's law. In obeying Raoult's law, the molecules of the component liquids should have similar polarities, and they should have similar sizes, and these two will mean that their interactions will remain uniform. For example, if you have liquids A and B, at least the way A interacts with A molecule should be the way A molecule interacts with B molecule, and should be the same way B interacts with the B molecule. Such that when you mix these two, there is no any bonds formed. There are no any intermolecular forces of attraction, extra forces of attraction is formed, so there will not be any heat change. And since they look the same liquids, then when you mix them, they should not change in volume. The volume of the solution should be the expected volume from the sum of the volumes of the component liquids. The examples of these liquids, actually, examples of liquids that can form examples of ideal solutions can be the common example we have been using, the hexane-heptane mixture, the hexane-heptane solution. We have benzene and methyl benzene. These are compounds which have almost the same characteristics. We have propan 1-ol, and propan 2-ol. These have almost the same polarity, and a few others. However, there are chances of the non-ideal solutions also becoming ideal when they are too dilute. We shall see those scenarios when we proceed. Can we briefly talk about the vapor pressure composition diagram? The vapor pressure composition diagram of an ideal solution. How can we plot the results that we get from different compositions of ideal solutions? see how the vapor pressure changes with composition. When you have two liquids, for consistency, let's still use hexane and heptane. From organic chemistry, we know this is C6H14, this is C7H16, meaning that basically, if you consider the sizes of these molecules, this should be less volatile than this. And from literature, the vapor pressure of pure hexane, is, let me call it P naught of hexane. The P naught of hexane is 16.09 kilopascals, and the P naught of heptane is 4.66 kilopascals. An indicator that this one can vaporize more than this. So, it means that when I have a solution of hexane and heptane at any composition, they must be able to vaporize, because at least both of them are volatile to some extent. So, we want to see if you are adding heptane to hexane, how does this vapor pressure keep changing from when you have 0% heptane in hexane until when you have 100% heptane. Remember, when you have 0% of heptane in hexane, it means that hexane is in its purest form because it does not contain any heptane. An indicator that the vapor pressure of hexane will be the P naught. So we can briefly put the P naught of hexane here. You can even put the figure 16.09. And as we have seen, hexane is more volatile than heptane. So it means that if I have pure hexane producing vapor of this vapor pressure 16.09, when I reduce hexane, for example, up to 90%, and I introduce in 10% of heptane, I am reducing the content of hexane. An indicator that I am trying to reduce the way it can vaporize. The vapor pressure of this mixture cannot be the same as the vapor pressure of pure hexane. Will it be lower or higher? That is the question you have to answer. Hexane vaporizes at 16.09. When I add heptane in it, does it vaporize more or less? The answer is it will have to reduce its vapor pressure because I have added in a component that has lower vapor pressure. So it will slightly reduce. It will slightly reduce. From this value up to some value, some lower value. When I continue like that until I continue until maybe I have 40% of hexane and 60% of heptane. Remember now, heptane will have overtaken hexane. This will be having much lower vapor pressure than hexane. It will be much lower. And when you are considering the vapor pressure of hexane, it will continue reducing until when it is 0. This should be a straight line. This should be a clear straight line. So this will be now the content of the hexane in vapor, the partial pressure of hexane, which we said it is always equaling to the mole fraction of hexane times the vapor pressure of pure hexane. This is how the partial vapor pressure of hexane will keep reducing. Likewise, when you are talking about heptane, heptane has vapor pressure which is slightly lower than 16.09. In fact, much lower. We can consider that to be P naught of heptane, which is 4.66. Also, when you have 100% heptane, hexane is 0. So it means that it will be the same graph, but for it starting from the other side. And it will be like that. So this will be the variation of partial vapor pressure of heptane, which will be equaling to the mole fraction of heptane times the vapor pressure of pure heptane. So that is how they will change. Why does it go up to 0? For example, for hexane, when there is 100% heptane, then hexane is basically 0. If it is 0, then it cannot vaporize. Likewise, when you have 0% heptane, there is no way you can measure its partial vapor pressure when it is not there. We need this curve here. We need this line here. The line that joins these 2 points. That is the line that will be indicating for us the total vapor pressure. It is showing the total vapor pressure, which will be equaling to partial vapor pressure of hexane plus the partial vapor pressure of heptane. So that is basically the vapor pressure composition diagram for an ideal solution. You can remove hexane and heptane and put anything. If you are, for example, using benzene and methyl benzene, you can change the labeling. But you don't forget that beyond the vapor pressure, when you increase vapor pressure, then you are increasing chances of having liquid state. When you reduce vapor pressure, you are increasing chances of having vapor phase. So it means that below this line, heptane will always exist as vapor. Above that line, heptane will always exist as a liquid. They are likewise on this line. But above this line of total vapor pressure, everything must be a liquid, and below that line, we shall find that partly we shall have hexane as the vapor and partly as heptane vapor. We also need to look at the boiling point composition diagram. So likewise, we are going to look at the boiling point composition diagram for an ideal solution. Remember, here we have said that this is the line that is showing how the partial vapor pressure of hexane changes in the mixture. Only and only hexane. That when you are reducing hexane, you are reducing its content in solution, and so its partial vapor pressure, its composition in the vapor keeps on reducing until when it is 0. Likewise, the one for heptane starts when it is maximum and reduces. So these are curves that show the variation of partial vapor pressures. Then the total vapor pressure is always higher than any vapor pressure of either hexane or heptane. Reason being, you have mixed the two. Both of them are vaporizing. It is always higher. What does this mean? Always something which can easily vaporize has a lower boiling point. Something which can easily turn into vapor has a lower boiling point. Something which can take time, which needs higher vapor pressure to turn into vapor phase, is less volatile and so has higher boiling point. An indicator that if this is 0% heptane, it is 100% hexane. If this is 100% heptane, it means that you have 0% hexane. So at this point, you can consider yourself having 100% of hexane, since the other one is 0. So if you have boiling point along this line, it will be boiling point of pure hexane. Hexane has higher vapor pressure than heptane. When we go to our boiling point diagram, shall we have hexane having higher boiling point or lower boiling point? Definitely, we shall have the boiling point of pure hexane lower than the boiling point of pure heptane. So, if this is the boiling point of hexane, then the boiling point of heptane will be higher. And as you are increasing the amount of heptane in hexane, what will happen to the boiling point of hexane? Remember, the interaction is uniform. You are trying to reduce hexane in the mixture. An indicator that the boiling point of the mixture will keep on increasing. Until when it reaches heptane. And also, the vapor, the composition of the vapor will keep also changing according to that curve. And that will generate for us the boiling point composition diagram for any ideal solution. The upper curve always is showing the change in the composition of the vapor. It is the opposite on the vapor pressure diagram, that at higher vapor pressure you have a liquid, but at higher temperature, in fact, to be very clear, let me also make this one temperature. At higher temperature, you will always have vapor. But at lower temperature, you will always have the composition of the liquid. Meaning that downwards, you must have purely liquid, and upwards, you have purely vapor. And that one will be our boiling point composition diagram for hexane-heptane mixture as an ideal solution. I have a simple question for you. Assume that this is 50% mark. 50. This is mark 50. Such that if you have here 50, then it is 50% heptane. An indicator that must be 50% hexane as well. When you get this mixture, it means that its liquid composition is X. The composition of that liquid is X. When you boil this liquid mixture, I want you to identify for me which composition of the vapor will you get. We have two possibilities. We have here A and we have here B. Of A and B, when you boil, make a solution of composition 50% hexane, 50% heptane, which vapor composition will you get? Let me make it clear. Boiling, and B represents the right composition of vapor produced by boiling mixture X. If you have mixture X at this point, you identify for me whether boiling that X will produce vapor of composition A, meaning 50% hexane, 50% heptane, or this other composition B. And after that, you give a reason for your answer. Make sure you give a reason, ensure that you convince yourself that you have understood, and keep in touch with us on our contacts and our YouTube channel. Keep watching us, keep sharing our videos, and help your friends to learn together with you. Don't forget to subscribe, and you keep notified of whatever we post for you. For today, we call it a lesson.